Hello friends, this is the third topic of our course, Isomerism in coordination complexes. Coordination complexes also poses different kinds of isomerism, which is grossly classified as structural and stereoisomerism. In structural isomerism, we find several kinds of subcategories. First one is ionization isomerism, second one is linkage isomerism, then coordination isomerism, and the fourth one is hydrate isomerism. Similarly, in the stereoisomerism category, there are two subclasses. One is optical isomerism, another is geometrical isomerism. So now we will try to explore each isomerism one by one. Now come to the different kinds of structural isomerism. The first one is ionization isomerism. This can be viewed as the different ions produced in solution when they are dissolved in a solvent. Say in these two molecules, in the first case, bromo ligand is inside the first coordination sphere and sulfate ion is outside the sphere, whereas they exchange their position in the second complex. Sulfate ion enters into the first coordination sphere and bromide ion goes outside the first sphere. So here, when they are dissolved in water or any other suitable organic solvents, in this case it will produce sulfate ion, whereas in this case it will produce bromide ion. So I think this is clear. Next comes to hydrate isomerism. Hydrate isomerism is the differences in the number of water molecules inside the first coordination sphere. Say here there are 6 water molecules and no chloride ion inside the coordination sphere, and the plastic charge of chromium is satisfied by this 3 chloride ion. Whereas in this case there is 5 water molecule and 1 chloride ion inside the first sphere, so there is outside 1 water molecule. Now there is you see the differences in number of water molecules, here 6, here 5, so they are hydrate isomers. Coordination isomers are observed for those cases where both the cation and anion are complex, or coordination complex. This molecule and this molecule have the similar formula, only they have exchanged the ligands. Here ammonia is with nickel and cyanide is with chromium, and here just take the reverse position, so they are coordination isomers. Similarly, linkage isomer takes place for an ambidentate ligand which has the capability of donating to the metal through different donor sites. In nitrito donor, the ligand donates to oxygen, whereas the same molecule, when it is attached through nitrogen, it is called nitro, so they are linkage isomers. Next come to the geometrical isomerism. This is as we find here, they comes under the category of stereoisomerism. Okay. In geometrical isomerism, the atoms of groups are arranged differently in space. So for a cis complex, the like groups are on the same side of the metal ion, whereas in the trans complex the like groups are on the opposite side of the metal ion. This is cisplatin and transplatin, very popularly known complexes. Here is an example for octahedral complexes, where in this cis molecule these 2 chloride ions are on the same side of the cobalt ion, central cobalt ion, whereas in this case chloride ions are on the opposite side of the central metal ion. Now the second category is the optical isomerism. They are basically characterized by enantiomers. Enantiomers are basically non-superimposable mirror image. Just like the mirror image of left hand is identical to right hand. So but left hand and its mirror image, they do not superimpose ever. Similarly, if this relation is also displayed by the isomers, then they will form a chiral molecule, and the physical properties, their physical properties are almost same, only they differ in the with the plane interacts. When they interact with the plane polarized light, their behavior becomes different. If one rotates the light by x degree clockwise, then other will rotate it by x degree anti-clockwise. So this is an example. Say if this is taken as a thilendiamine, so cobalt Bc dichloro Bc thilendiamine cobalt 2, that form a that forms a an optical isomerism. They have their optical isomers in octahedral geometry. So thank you, and hope you enjoyed this lecture and maybe of your work. Thank you very much.